Hello friends, welcome to my lecture on Cauchy's integral theorem. We will have two lectures on this theorem. You will see that this theorem is a very important result in complex analysis. We will need two results which we have given in the following two examples. First is that if fz is equal to a constant k and C be any rectifiable curve joining 2 points z naught and z in the complex plane, say suppose we have two points z naught and z in the joining which are the end points of a curve C in the complex plane, and this is the direction of increasing values of t. Then integral over C k times dz, which is limit n tends to infinity S n is equal to k times z minus z naught. Now, in our last lecture we had seen that how to evaluate integral over C f z dz. What we had done was we divided the curve C into n parts by means of points z naught, z1, z2 and then say zm minus 1, zn, zm and then zn. Okay. So, zn is equal to here is capital Z, and then we had chosen arbitrary points zeta 1 here, zeta 2 here and say zeta m here between zm minus 1 and zm, and then between zn minus 1 and zn we had chosen zeta n, and then we have formed the sum Sn as sigma m equal to 1 to infinity 1 to n f zeta m delta zm. This was defined as Sn. Okay. Then we had said that let n go to infinity in such a way that maximum of mod of delta z k 1 less than or equal to k less than or equal to n tends to 0, then limit n tends to infinity S n is equal to integral over C f z dz. Okay. So, here we are given f z equal to k. So, integral over C k dz will be equal to limit n tends to infinity S n, which is equal to limit n tends to infinity sigma m equal to 1 to n f zeta m delta zm, where maximum of mod of delta z k 1 less than or equal to k less than or equal to n goes to 0. Now, this is equal to now we are given f z equal to k for all z belonging to C. So, f zeta m is a point on the curve C. So, f zeta m equal to k for all m equal to 1 to n. So, we shall have limit n tends to infinity maximum of mod of delta z k 1 less than or equal to k less than or equal to n goes to 0 sigma m equal to 1 to n in k delta zm. Okay. Now, recall that delta zm is equal to zm minus 1. Okay. So, let us find the value of this sum sigma m equal to 1 to n k is a constant delta zm. So, k can be written outside the summation and then delta zm is zm minus 1 sigma m equal to 1 to n. Okay. When you will expand this, what you get is k times z1 minus z naught, then z2 minus z1 and so on zn minus 1. Okay. So, what will happen? Z1 will cancel with Z1, Z2 will cancel with Z2, and so on. Zn minus 1 will cancel with Zn minus 1, and what we will get? K times Zn minus Z naught. Okay. And Zn is equal to Z. Okay. So, what we will get? This will be limit n tends to infinity maximum of mod of delta Z k goes to 0. This is nothing but k times Z minus Z naught. So, you can see that summation k m equal to 1 to n k times delta Z m is k times Z minus Z naught. Okay. So, whatever be the subdivision of the curve C n by n by taking n points, okay, this value remains constant, it does not depend on n. Okay. So, this is limit is equal to k times Z minus Z naught. Okay. So, this is what we get, integral over C k dz is equal to k times Z minus Z naught. Now, suppose this curve C is a closed curve. If C is a closed curve, then capital Z will be equal to Z naught. So, if C is a closed curve, simple closed curve, let me say, a simple closed curve means a closed curve which does not intersect itself. So, in this curve, if the Z and Z naught they are same, they meet, then this will be a closed curve. So, when so then what will happen? Z will be equal to Z naught, and so integral over C k dz will be equal to 0. Okay. So, in case of a closed curve, when C is a closed curve, we will need this result later on when we prove the Cauchy's theorem. Okay. Now, let us go to another example. Now, let us consider f z equal to z. Okay. So, here we take f z equal to z identity function f z equal to z, and we shall find the value of the integral over z naught to z. Again we are taking the same curve, say joining the points z naught and z in the complex z plane. Okay. We shall show that it is half of capital Z square minus Z naught square. So, in particular, if C is a closed path, that means Z naught becomes equal to Z, then you see that the value of the integral is 0. So, what we do here, let us again recall the definition of the integral of f z, integral over C f z dz is equal to limit m n tends to infinity S n, where maximum of mod of delta Z k 1 less than or equal to k less than or equal to n goes to 0, and S n is sigma m equal to 1 to n f zeta m delta Z m. Okay. This is Z m minus 1, let us say, and this is Z m. Zeta m is a point in between Z m minus 1 and Z m. Now, zeta m is chosen in a completely arbitrary manner in the interval Z m minus 1 to on the curve between Z m minus 1 and Z m. So, we can take zeta m to be Z m minus 1 as well as zeta m to be Z m. Okay. So, taking zeta m to be Z m minus 1, okay, we have f zeta m equal to f Z m minus 1 equal to Z m minus 1, because we are taking f z equal to z. Okay. So, then S n equal to sigma m equal to 1 to n Z m minus 1 into delta Z m, but delta Z m is Z m minus Z m minus 1. So, what we have is this. Okay, this is what we have. Now, similarly, let us take zeta m now equal to Zm. Okay. First we have taken zeta m equal to Zm minus 1, now we take zeta m equal to Zm. So, then the sum sigma m equal to 1 to n f zeta m delta Zm, let us call as Sn star equal to sigma m equal to 1 to n f zeta m equal to f Zm. So, we will have Zm here and then delta Zm. So, this will be summation m equal to 1 to n Zm into Zm minus 1, Zm into Zm minus 1. Okay. Now, let us add this, let us say call as equation 1, this is equation 2, then from 1 and 2 Sn plus Sn star is equal to sigma m equal to 1. So, let me write Sn first. So, m equal to 1 to n. So, that means Z naught, then we have Z1 minus Z naught, then we have Z1, Z2 minus Z1, okay. Then Z2 into Z3 minus Z2 and so on. When you put m equal to n, we get Zn minus 1 into Zn minus 1. This is the value of Sn, okay, plus Sn star. Sn star, we put the value of m equal to 1 to n. So, Z1 into Z1 minus Z naught, Z2 into Z2 minus Z naught and so on, Zn into Zn minus 1. Okay. Now, you can see when you add these two expressions, you see Z naught Z1 will cancel with Z naught Z1, okay. Then Z1 Z2 here will cancel with this is Z2 minus Z1. So, Z1 Z2 will cancel with Z1 Z2 here and so on, and what will happen? So, Z1 Z2 Z3 they will all cancel, Zn minus 1 will cancel with Zn minus 1 here, and then what we will have here minus Z naught square, then we will have minus Z1 square, Z1 square will cancel with Z1 square here, Z2 square will cancel with Z2 square here and so on. So, this will give you last term, the terms which will be left will be Zn into Zn, that is Zn square minus Z naught square. Okay. Now, let us take the limit as n goes to infinity, okay. Then what will happen? Limit n tends to infinity such that maximum of mod of delta Zk maximum mod of delta Zk goes to 0, okay. Sn plus Sn star by our definition is equal to integral over C, limit of Sn is integral over C f z dz, and limit of Sn star is also integral over C of z dz, because zeta m can be chosen anywhere on the curve between Zm minus 1 and Zm. For one time we have chosen it as Zm minus 1 and the other time we have chosen it Zm. So, this will give us the same limit, okay. So, plus integral over C f z dz, and this is then equal to Zn square, and Zn is what? Zn coincides with Z. So, this is Z square minus Z naught square. This quantity is independent of Z, independent of n, okay. So, Z square minus Z naught square, okay. So, twice integral over C f z dz is equal to Z square minus Z naught square, or we can say integral over C f z dz equal to half of Z square minus z naught square. So, this is how we prove this result. When this curve is a closed curve, that is z naught and zn coincide, z naught and capital Z coincide, then z square will be equal to z naught square. So, we will have the integral equal to 0. So, integral of f z equal to z when C is a simple closed curve is 0. Now, if f z, and let us now list the basic properties of complex line integral. If f z and g z are integrable along a curve C, okay, rectifiable curve C, then integral over C f z plus d z g z d z is equal to integral over C f z d z plus integral over C g z d z, okay, and integral over C k f z d z is equal to k times integral over C f z d z, where k is a constant. So, k is a constant here, complex constant. Now, integral over z naught to z, if you take 2 points z naught and z and you join them by a curve, then integral along z naught to z f z d z will be negative of integral from z naught to z. That is, when you reverse the signs of integration along C, suppose this is your curve C, okay, and this is your z naught point, this is your capital Z point. Suppose you are integrating from z naught to z, okay, that is, you get this integral, and when then you integrate from z to z naught, okay, that means you reverse the sign of reverse the signs of integration, then there will be a change of sign. So, integral over C f z d z is integral over C 1 f z d z plus integral over C 2 f z d z. If we decompose path C into two portions, suppose this is your path C, okay, you decompose it into two parts, say this is A, this is B and this is C, okay. You decompose it into two portions, say C 1 is the arc of the part of the curve from A to B, and C 2 is the part of the curve from B to this is your B, yeah, this is your B, this is your curve C, okay, curve C. So, this is curve C, okay. So, integral from A to B plus integral from B to C along the curve will be equal to integral over C, okay. So, now these results can be easily established by using the definition of the line integral as the limit of a sum, okay. So, they can be taken as an exercise. I will prove that the mod of integral over C f z d z is less than or equal to m into L, where L is the length of the path C and m is a constant such that mod of f z is less than or equal to m. Now, let us see when we had considered the curve C in the complex z plane, so joining the points z naught and z be divided into n parts, by means of points z1 z2 zn minus 1 and zn, okay. And then we had taken arbitrary points in a completely arbitrary manner between z naught and z1 as zeta 1, then zeta 2 between z1 and z2, and then with zeta m between zm minus 1 and zm, and we form the sum Sn equal to sigma m equal to 1 to n f zeta m delta zm, okay. And the limit of this Sn as n goes to infinity when in such a way that mod of delta zm, maximum value of mod of delta zm goes to 0 when m varies from 1 to n, then that gives you the integral over C f z d z, okay. So, let us see, mod of Sn is less than or equal to sigma m equal to 1 to n mod of f zeta m into mod of delta zm, okay. Now, mod of f z is less than or equal to m for all z on C. So, mod of f zeta m will be less than or equal to m for all m equal to 1 to n so on up to n, because zeta m belong to curve C, okay. So, this is less than or equal to m times sigma m equal to 1 to n mod of delta zm. What is mod of delta zm? Let us look at this. You see, this is mod of delta zm. Let me show you like this. This is zm minus 1, this is zm, okay. Then mod of delta zm is mod of zm minus Zm minus 1. That is the distance between the complex number Zm minus 1 and Zm. So, this is the mod of delta Zm, this is mod of delta Zm. Okay. That means the length of the chord joining the points Zm minus 1 and Zm. Okay. So, this is the sum of the lengths of the chords which join the points Z0 to Z1, Z1 to Z2 and then so on Zn minus 1 to Zn. Now, if we let n go to infinity in such a way that, let n go to infinity in such a way that maximum of mod of delta Zm, where m varies from 1 to n, this goes to 0. So, you go on increasing the number of points that divide the curve into n parts, okay, in such a way that the maximum length between any two points goes to 0, okay, between the points of the subdivision goes to 0, then what will happen? Limit n tends to infinity, mod of Sn will be less than or equal to m times limit n tends to infinity sigma m equal to 1 to n mod of delta Zm. This will be equal to m times L. That is, the sum of the lengths of the chords will tend to the length of the curve C. Okay. So, limit n tends to infinity mod of a sigma m equal to 1 to n mod of delta Zm will be equal to m into L. And we know since limit n tends to infinity Sn is equal to integral over C f z dz, we have limit n tends to infinity mod of Sn is equal to mod of integral over C f z dz, because this can be easily established, because mod of Sn minus mod of integral over C f z dz by triangle inequality is less than or equal to mod of Sn minus integral over C f z dz. Okay. So, when integral over C f z dz tends to Sn tends to integral over C f z dz, mod of Sn tends to mod of integral over C f z dz. So, this limit is nothing but mod of integral over C f z dz. So, this actually this gives us mod of integral over C f z dz less than or equal to m into L. So, this curve, this property is also going to be used in the proof of the Cauchy integral theorem. Okay, now, let us define what is a simply connected domain. Suppose a domain D in the complex plane is called a simply connected domain if every simple closed curve in D, as I defined earlier, a simple closed curve is a closed curve which does not intersect itself. So, a closed curve in D without self intersections encloses only points of D. Okay. A domain which is not simply connected is called a multiply connected domain. For example, you can see the interior of a circle. Okay. A circle is a closed curve and it does not intersect itself. So, it is a simple closed curve. If you take a rectangle, it is a closed curve which is a simple closed curve because it does not intersect itself. Let us take a ellipse. Okay. It is also a simple closed curve. They are all simple closed curves, or you can take a square. They are all simple closed curves. The interior of a simple closed curve is a simply connected domain. In general, the interior of a simply closed curve is a simply connected domain. If you take a circular ring, okay, this is the domain whose boundary consists of two parts, okay, the inner circle and outer circle. Okay. So, this is not a domain shaded region is not a simply connected domain because this because of the fact that if you take any curve in this, okay, it cannot be shrunk to a point without leaving the domain. Actually, we say that a simple closed curve is one which can be shrunk to a point without leaving the domain. So, here you can see if you take a closed curve in the shaded region and you go on shrinking it, it cannot be shrunk to a point without leaving the domain. So, it is not a simply connected domain. There are two boundaries of this region. So, this is called a doubly connected domain. A domain which has p boundaries will be called a p connected domain. In fact, a bounded domain is called p fold connected if its boundary consists of p closely connected such boundaries without common points for the annulus. So, this is annular region. Okay. The region bounded by two concentric circles is an annular region. So, this is called a doubly connected domain. The boundary consists of two circles having no point in common. So, if a domain is not simply connected, it will be called a multiply connected domain. Sir, for example, you consider a domain like this. You can see here if you take this region, this is not a simply connected domain, because if you take a closed curve like this, okay, it cannot be shrunk to a point without leaving the domain. So, the interior of this closed curve is not simply connected, and its boundary of this region consists of 1, 2, 3 and 4 parts. Okay. So, it is 4 connected. P connected means 4 connected domain. It is a multiply connected domain. A domain D will be called bounded if it lies entirely in some circle about the origin. That means, if you take a domain, it will be called a bounded domain if you can draw a circle with center at the origin of some radius r, such that the given domain lies completely inside it. Say for example, you take this as origin, you can draw a circle like this, okay, in which this lies. So, if you can construct a circle with center at the origin of some radius r, such that the domain D lies completely inside it, then the domain D will be called a bounded domain. Now, Cauchy integral theorem: if f z is analytic in a simply connected bounded domain D, then for every simple closed path C in D, integral over C f z d z is equal to 0. Now, you can see how powerful result is this Cauchy integral theorem. It says that you take any simply connected domain, bounded domain, if f z is analytic there, then you take any simple closed path in C in D, integral over C f z d z equal to 0. For example, let us consider f z equal to e to the power z. We know that it is an analytic function, it is analytic for all z in the complex plane, for all z in C in the complex plane, z plane. So, the theorem says that you take any simple closed path in the complex plane, okay, any simple closed path, okay, any simple closed path, whether it is circle or it is ellipse or you take a square or you take a rectangle, okay, the integral of e to the power z along that path is equal to 0. So, integral over C e to the power z dz equal to 0, where C is a simple closed path, C is any simple closed path in D. D means the whole complex plane, that is the whole complex z, whole z plane. You can take any polynomial, f z can be any polynomial in z. The same situation, the integral over C f z dz will be 0. You can take f z to be sin z or f z to be cos z, or you take f z equal to sin hyperbolic z or cos hyperbolic z. They are all analytic functions for all z, and so integral of f z, okay, will be 0, integral of f z dz will be 0 for along any simple closed curve in the complex plane for these functions. Okay. So, this is a very powerful result. Let us see how we prove this. We begin with the case. First, let us consider the case where the simple closed curve C is the boundary of a triangle. You can see the triangle boundary of the triangle is a simple closed curve. It is a closed curve and it does not intersect itself. Okay. So, C here is the boundary of a triangle. Now, what we will do? We will show that integral over C fz dz is equal to 0. Okay. We will show that integral over C fz dz equal to 0, where C is the boundary of a triangle. Now, so integral over C fz dz can be written in. So, here let me say this is A, this is B, this is C, this is D, E, F. Okay. Then integral over C fz dz will be equal to what? Integral over C fz dz will be equal to integral over A d b e c, A d b e c f a f z. Okay. A d b e c f a. Okay. Now, I can write it as integral over A d f a plus integral over d b e d plus integral over E c f e plus integral over E d f e. Okay. So, there are 4 triangles A d f a, then d b e d, then E d f e, then E c f e. Okay. Now, I say that integral over C f z dz, which is A d b e c f a, is equal to this. Why? Because when we find the integral over A d f a means integral over A d f a means integral over A d plus integral over d f plus integral over f a, and integral over d b e d means integral over d b plus integral over b e plus integral over E d. Integral over E c f e similarly will be E c f e. Okay. So, E c plus C f plus integral over f e, and then lastly integral over E d f e. This is equal to integral over E d plus integral over d f plus integral over f e. This along the triangle E f c we are moving anti-clockwise. So, E f c e, E f c e it should be. So, here E of C. Okay. So, we will have here E of f c c e. Okay. E f, then f c, then c. Okay. Now, here we have E d, okay, E d f e. So, E d f e. So, E d plus d f plus f e. Now, let us add all these integrals. So, what we will get? We will write here this way. Okay, let us see. What I am doing is A b, I am moving along this direction, then this direction, and then this way. So, integral over E f d e. Okay, so E c f e, so E c and then integral over C f, then integral over f e. So, this will be anticlockwise, okay. And here in the case of the triangle, so E f f d and then d. Now, whether they cancel, you see, so d f cancels with f d because they are in opposite directions, then d e cancels with E f cancels with f e and E d cancels with d, okay. And what we have A d plus d b, this A d plus d b means A b, okay. And then we have b e plus E c, so b e plus E c, that means that integral over b c, and then we have two more C f and f a, okay, that is integral over C a. So, integral over C f z d z, which is integral along a b plus integral along b c plus integral along C a, can be written as the sum of 4 triangles, and these triangles have been made by taking d, e and f as the midpoints of the sides a b, b c and C a. So, these are d, e and f are midpoints of a b, b c and C a. So, by taking d, e and f to be the midpoints of the sides a b, b c and C a, okay, and then joining them, joining d to e, then e to f and f to d, we find 4 triangles, okay. And we see that integral over the triangle a b c a, integral along the path a b c a is equal to the sum over the boundaries of the 4 congruent triangles. These are all 4 congruent triangles, okay. So, let C be the boundary of the triangle, let us orient it in the counterclockwise sense, okay. By joining the midpoints of the sides of the triangle, we subdivide it into 4 congruent triangles, okay. So, let us name those congruent triangles as C 1, C 2, C 3 and C 4, okay. So, C 1 is A D F A, this is C 1, A D F A, okay, this is C 1. C 2 is D B E D, D B E D, this is C 2. C 3 is E F C E, this should be E C F E, E C F E, okay. So, E C F E, this is C 3, okay, this C 3, and C 4 is this one E F D E, okay. Okay, E F D E, this one, okay. So, this fourth triangle, okay. So, this is how we write it, and then what we do is integral over C f z d z is equal to integral over C 1 plus integral over C 2 plus integral over C 3 and C 4 f z d z, where C 1, C 2, C 3, C 4 are boundaries of the 4 congruent triangles, okay. Mod of integral over C f z d z by triangle inequality is less than or equal to mod of integral over C 1 f z d z plus mod of f z d z over C 2, mod of f z d z integral over f z d z over C 3 and mod of integral over C 4 of f z d z. So, now what we do is, let us say that C 1 be the boundary of that triangle which corresponds to the term on the right side of this equation, okay, having the largest value. If there are 2 or more such terms, then C 1 is the boundary of any of the associated triangles, okay. So, then what we will do, this will be mod of integral over C f z d z will be less than or equal to 4 times mod of integral over C 1 f z d z, because C 1 is the boundary of that triangle whose integral over C 1 is the largest, okay. So, each of the terms on the right side of this equation will be less than or equal to mod of integral over C 1 f z d z, okay. So, what we have here, you see, this was the situation. Out of these 4 congruent triangles, we have taken that triangle as C1, okay, whose integral of fz along that C1 is having the maximum value. Okay. So, then that C1 is now again subdivided into 4 congruent triangles by taking the midpoints of the sides of that triangle C1 and joining them. Okay. So, by similar process, by joining the midpoints of the sides of the triangle bounded by C1, we obtained similarly a triangle with boundary C2 such that mod of integral over C1 fz dz is less than or equal to 4 times mod of integral over C2 fz dz. Now, combining this and this equation, okay, these two equations, we arrive at mod of integral over C fz dz less than or equal to 4 square mod of integral over C2 fz dz. Now, continuing this process, okay, we obtain a sequence of triangles T1, T2 and T3 and so on with boundaries C1, C2 which are similar triangles and such that Tn lies in Tm when n is greater than m. Okay. You can see C1 C2 lies in C1, C3 lies in C2 and so on. So, when n is greater than m, Tn lies in Tm. Okay. And mod of integral over C f dz will be less than or equal to 4 to the power n mod of integral over C n fz dz. Now, let z naught be the point which belongs to all these triangles. Actually, we have here a nested sequence of triangles. So, let z naught be the point which belongs to all those all these triangles. Then we have assumed that f is analytic. Okay. So, f is differentiable at z naught. Okay. So, f z equal to f z naught plus z minus z naught f prime z naught plus eta z z minus z naught. You see, we have f prime z naught equal to limit z tends to z naught f z minus f z naught divided by z minus z naught, or we can write it as f z minus f z naught by z minus z naught minus f prime z naught equal to eta z. Okay, we can write like this, where eta z goes to 0 as z goes to z naught. So, by definition of derivative we have this equation. This can be alternately written like this and we then can write it as f z equal to. So, this gives you f z equal to f z naught. By multiplying the equation by z minus z naught, we have f z naught plus z minus z naught into f prime z naught plus eta z into z minus z naught. Okay. Now, eta z goes to 0 as z goes to z naught. So, what will happen? We will, for any epsilon greater than 0, we can find a delta greater than 0 such that mod of eta z is less than or equal to epsilon whenever mod of z minus z naught is less than delta. This follows from the definition of limit. Now, from the equation 2, okay, let us see how we get this equation. Okay. Let us integrate this equation 2. Okay. Let us integrate this along the curve C, okay, along the curve Cn. Okay. Cn is the boundary of the triangle Tn. So, what we will have here, when we integrate, we have the equation f z equal to f z naught plus z minus z naught f prime z naught plus eta z z minus z naught. Okay. So, let us integrate over Cn f z dz, then this is equal to integral over Cn f z naught dz plus integral over z minus z naught f prime z naught in integral over Cn dz plus integral over Cn eta z z minus z naught dz. Okay. Now, we have already shown that if C is a closed path, if C is a closed path, closed curve, then integral over integral of k over C, okay, is equal to 0. This we have already proved. Here f z naught is a constant quantity, okay. So, integral over Cn f z naught dz equal to 0, okay. And then here f prime z naught is a constant quantity, I can write it outside the integral. Now, integral over Cn z minus z naught dz can be written as integral over Cn z dz minus integral over z naught dz Cn, okay. Integral we have also proved that integral over C z dz equal to 0 when C is a closed curve. Simple closed curve, okay. So, integral over Cn z dz is equal to 0 because Cn is the boundary of the triangle Tn, okay, which is a simple closed curve. So, this is equal to 0, integral over Cn z naught dz is also 0, this by using this result. So, this is 0, this is 0, okay. So, we have integral over Cn eta z z minus z naught dz, okay. So, this is equal to what we have here 0, this is 0. So, integral over Cn z minus z naught into eta z dz. So, this integral, okay, this integral is equal to this integral, this is 0 and this is 0, okay. So, integral over Cn f z dz is equal to this. Now, let us take n to be so large that the triangle Tn, okay, the triangle Tn whose boundary is given by Cn lies in the disk mod of z minus z naught less than delta. We have already found a delta corresponding to epsilon because eta z goes to 0 as z goes to z naught. So, let us take the disk mod of z minus z naught less than delta. Let us say this is your z naught, construct this circular disk, this is mod of interior of this, okay, is mod of z minus z naught less than delta. So, take n to be so large that the triangle Tn lies in the, because z naught lies in any every triangle Tn, okay. So, when n is very large, Tn will lie inside this disk mod of z minus z naught less than delta. Let us say Ln be the parameter of Cn. If Ln is the parameter of Cn, then Ln will be equal to L by 2 to the power n, where L is the parameter of C. Why? Because this was your triangle ABC, okay. By joining the midpoints of the sides of the triangle, we obtained 4 congruent triangles, okay. Since we joined the midpoints D, E and F, okay, each of these 4 congruent triangles has half of the perimeter of the ABC triangle. So, the triangle ABC, if it has perimeter L, okay, then each of these 4 congruent triangles will have perimeter L by 2. So, this is when n equal to 1. If you take now let us say C1 is that triangle along which the integral of fz is having the largest value, and let us say this is C1 triangle. So, again you join the midpoints here, you get this, okay. So, if since its length of ADF is L by 2, then here the C2 triangle will be that triangle along which the integral of fz will be having maximum value. So, if C2 is this triangle, then its perimeter will be half of the perimeter of ADF, that means L by 2 square. So, when n is equal to 2, you will get Ln equal to L by 2 square. So, in general Ln will be equal to L by 2 to the power n, where Ln is the parameter of Cn, okay. Now, mod of z minus z naught, okay, mod of z minus z naught is less than Ln. You see here, suppose this is your this is your triangle Tn, okay. This is your triangle Tn whose boundary is Cn, this boundary is, let us say, Cn, okay. You take any point z here, z naught is a point which lies inside the circle inside the triangle Tn. So, the length of this line segment joining z naught to z, this length of the line segment z naught to z will always be less than the perimeter of Tn, okay. So, mod of z minus z naught is less than the perimeter of Cn, that is Ln, and Ln is equal to L by 2 raised to the power n. L by 2 raised to the power n is less than delta, okay, because the triangle Tn lies inside the disk. Okay. So, mod of z minus z naught less than delta. So, mod of z minus z naught is less than ln, ln is L by 2 raised to the power n, which is less than delta. This will be true for all z on Cn. Okay. Hence, mod of integral over Cn f z dz. Now, let us come to this mod of integral over Cn f z dz is equal to this quantity. Okay. This one, let us come to this. Okay. So, mod of integral over Cn f z dz will be less than integral over Cn mod of eta z mod of z minus z naught mod of dz. Okay. Mod of eta z is less than epsilon whenever mod of z minus z naught is less than delta. Okay. So, this is epsilon, and mod of z minus z naught is less than L by 2 raised to the power n. Integral over Cn mod of dz, okay, is nothing but the length of Cn. Okay. So, this is equal to L by 2 raised to the power n. Okay. So, this is L by 2 raised to the power n. So, epsilon into L square 4 to the power n. Okay. This is L square over 4 to the power n. Now, mod of integral over C f z dz, this be found to be less than or equal to 4 to the power n into integral over Cn f z dz mod of this. Okay. And this is less than or equal to epsilon into, so this is 4 into 4 to the power n into epsilon L square by 4 to the power n. So, this will cancel and we will get epsilon L square. Now, epsilon can be made arbitrarily small because it is arbitrary. So, that is taking epsilon to be arbitrarily small. Okay. We arrive at integral over C f z dz equal to 0. So, when C is a triangle, okay, C the boundary this curve C is the boundary of a triangle, okay, we found that integral over C f z dz equal to 0. Now, let us consider the case 2 where C is the boundary of a closed polygon. You can see, suppose this is the polygon, this is A, B, C, D, E. This is my polygon A, B, C, D, E. Okay. What I do is I join B to D and A to D. Okay. And then I see that integral over A, B, C, D, E, A, B, C, D, E, A f z dz. Okay. So, I convert it into 3 triangles 1, 2, 3. Okay. And what I notice is that integral over A B d A plus integral over B C d B plus integral over d E A D. Sum of these 3 integrals is equal to integral over A B C D E A. While finding integral over A B D A and then B C D B and then C D D E A D, okay, we will be moving along B D in the opposite directions, B D and D B, and then here again along D A in the opposite directions, A D and D A. So, integral along A D and D A will cancel. This will be equal to 0 and similarly integral along B D. So, since this is equal to 0 and this is equal to 0, okay, this sum of these 3 integrals will be equal to this integral. Okay. Now, integral A B d A, we have already proved that if C is the boundary of a triangle, then integral along C is equal to 0. So, integral along A B d A will be 0, integral along B C d B that will also be 0, and then integral along D E A D that will also be 0, and we will get 0. So, we subdivide the polygon into triangles, the integral corresponding to each such triangle by using case 1 is 0, and so the sum of these triangles is equal to 0, and this proves the Cauchy integral theorem for the case where C is the boundary of a closed polygon. Now, in the next lecture we shall consider any simple closed curve C in the complex z plane and show that the integral of f z along that simple closed curve C is equal to 0. With this I would like to end my lecture. Thank you very much for your attention.